Hello everybody, my name is Steven De Meester indeed from Ghent University. So our task was to assess the sustainability of biorefineries. So the first question is, ProSUD says sustainability assessment of technologies. So then we first have to think, what are technologies, how do you define them? And Joao, if you could agree. So basically biorefineries, they process biomass into different applications, and biomass is a rich resource, so you can make really a lot of things from that. So it's a whole economy with a different resource. So if the technology is biorefineries, then I think we can't assess it as a whole, because there are so many different applications and there's no common reference to compare it. So that's why actually we started thinking, well, we should maybe go back to the functional unit approach. So that's what we did in the end. And if you could click. Basically, the technology of biorefineries, they can make a lot of products, so we tried to choose different products from the different applications. So one is from anaerobic digestion, which makes bioenergy. One is bio-based PVC, which is a plastic, and then alkyd resins, which will be presented from Lex after this one. And if we know bio-based products, if you have experience in doing life cycle assessment or environmental assessment of bio-based products, then we know that the agricultural phase is really important. So that's why we also included the agricultural phase and collected foreground data of the agricultural data set, instead of relying on the databases. So, of course, we say new emerging technologies, but you have to have a starting point to start assessing. There has to be some knowledge, some practical experience. So I first gonna talk about the anaerobic digestion case, and we started with two real factories that are there. This one is in Germany, yes. So they produce silage maize. So the first step is the agricultural phase, and then it's actually a quite simple installation, just with a digester, a gas bag, and a combined heat power, and they make electricity. And what's really important in this one is that the anaerobic digestion, they produce, apart from the energy, they also produce digestate, so which can be used in different applications, but in many cases it's used as a fertilizer on the field. So it flows back into your system. And if you want to use databases that can be purchased, then there's no such thing as agriculture with digestate fertilization. So that's why we also focused to gather this foreground data set. But I won't go deeper into that. And then the second facility was in Belgium. It's a bit more complicated. It processes domestic organic waste. If you click down. So what you need first, you don't need the upstream production of the agriculture directly, but you need the collection, and then you need pre-treatments. There are separations. Then there's a digester, and then there comes post-treatment and wastewater treatment. And what is then our functional unit? Because we had to go back to the functional unit. At the current moment, we don't see another way to assess complete technologies. So we took the 2030 electricity production by coal electricity, which is the 387 terawatt hours per year. But we were thinking also, can we introduce market mechanisms in here? But to be honest, most bioenergy options, they are not profitable. So there is no market diffusion or things like that. That is just if you have more subsidies, which are different in the different countries, then there are more bioenergy installations. So that's why we took this functional unit. And of course, this is the starting point, the technologies that are there. But an important thing in the ProSUD project is the prospective aspect. And then basically how do you get the prospective aspect in your assessment? Basically, it's by changing your inventory. The technologies will become more efficient, or there will be changes in process chains. And that's also what we tried a bit to include in our assessment. So the first thing was for example, we had a workshop with specialists. What will happen with the technology? The first thing that they said was, well, the biological efficiency of anaerobic digestion will not increase, probably, or not that much, but the equipment around it, that will become more efficient. The transport will become more efficient. The leaching and the leaks in the pumps and for the methane emissions, they will increase. And also what's now a problem for anaerobic digestion is that the heat, there's a production of biogas which is burned. In most cases it's decentral, so the heat is not always used, and that will change in the future. So one way to integrate that prospective aspect is to make your electricity consumptions and all your equipment more efficient. So that's one way how we did it. And then the second way, if you click there, this is actually from another case study, but I still wanted to present it. There are two ways, as I said, there are two ways to include the prospective aspect, and one, which is also elaborated in the project, is to develop engineering models, to really start to model the processes. Because if you don't have the starting point of the digestion facilities as we had them, then you can't start making them more efficient because you don't even have that data. So then you need to start really puzzling your plant together with different processes. And in task 1.2 of our of the process project, we developed engineering modules to do that. And we tested that in a case study, but that's reading in the deliverable, and I won't go deeper into that. But here, that's the different processes which we included, but there's a longer list, but we weren't able to validate them all. And here you can say they calculated over the real value. So we did first the prospective assessment and then check in reality how does that comply with the real data. And you see a mixed result. For some processes we had good result, and for others we had a bad result. So we also, in Work Package 2.2, there's a similar tool for economic assessment. So because for the input in the full sustainability assessment, you need an environmental, so a mass and energy balance, and you need the economic data. And there's also a tool developed to estimate the life cycle costing data. And that's what you see here. Of course, we couldn't present the y-axis with the real numbers because that's confidential, but we were able to see them and to use them for the test. So here you can see the CENT, so the life cycle costing tool is called CENT. Prediction, and here you see the real value. This is of the domestic organic waste valorization, and here you see the prediction of the small-scale agricultural setup, so the digestion of silage maize. So, and in the case of the domestic organic waste, you can see that the prediction was relatively good. But in the case of the anaerobic digestion of silage maize, then the prediction was a bit worse, because the tool, it accounts for overheads of if you build a facility for engineers and stuff, but of course the farmers, they built a part of the factory themselves. So that lowers the overhead, and that makes that the prediction is a bit less correct. So, and then we go to the results. I won't go too deep into all of them. Here we use the Condorcet, so the outranking methodology, which is basically giving more points to the technology with the best score. Basically, it's a bad thing because you lose a bit of information, because in some category one can be really good and one can be really, really bad, or they can be close to each other, and you don't see that here. But on the other hand, it has the advantage that you don't struggle with system boundaries and all these aspects if you want to integrate the different dimensions. So what can we see here? For these lower three are the previously called environmental impacts. And then the anaerobic digestion performs best, especially for the impact on exhaustible resources and the impact on human health. The silage maize digestion has the best performance, because here also quite some fossil fuels are used for the collection of the waste. And here the impact on the natural environment, the organic waste digestion performs best, because here you have the silage maize, you have the agricultural phase with the eutrophication and impacts related to that. And then, of course, the reference system is dominated by the coal, the impacts from the coal. So there's a lot of impact of climate change as well. So that performs worse. But what is surprising here is the impact on prosperity. So that's basically, we are used to doing environmental assessments, but the impact on prosperity is relatively new for us. So what was interesting is to see that if you use fossils, you have the average result, so it's the purple one there. And if you use silage maize, then there's an increase in prosperity. And this, in principle, is logic, because if you do agriculture, instead of just pumping up fossil fuels, you need a lot of more economic activity. So that's really interesting to see that the economy evolves and it increases. Economic activity increases. But on the other hand, if you valorize your waste, so that could be questionable from a sustainability point of view, but it's not good for the economy because you're using a resource more efficiently. So you don't stimulate any other sectors. So that's a bit how the economy works, I think. If you use more resources, then you get more money. But if you use the resource more efficiently, you're GDP number lowers. So that was one of the conclusions we had here. The second case study was it was bio-based PVC compared to fossil-based PVC. So that's the fossil-based PVC, how it is done now, and that's actually, you could say it's prospective because it was a plant. It was together with Solvay that they would have built in Brazil, but in the end they didn't build it. So we got the numbers and projections from them, so the data from them. And here what we did was include also the sugarcane production in Brazil, and we also included that in our foreground system because Brazil is a developing country, and basically the data sets that come from there, they are developing. So the agricultural phase and all these different processes, they also become more efficient. And if you move up, you can see here also mixed results. For the natural environment and exhaustible resources, the renewable PVC or the bio-based PVC performs best. But if you look at human health, then the reference of the fossil-based PVC performs best. And why is that? Because when they produce sugarcane in Brazil, they also burn a part of the PVC before they harvest to make it easily harvestable. So then you have a lot of particulate emissions. And that's a bit why, in this case, the bio-based PVC has a worse impact on human health. And also social well-being in general. There's, in the statistics, there's child labor and forced labor associated with agriculture, and that's why often in the prospective or the bio-based systems, they perform worse on the social well-being. I'm finished. Yeah. Indeed. So what are my conclusions? So we tested the methodologies, and we also tested, I think, which is quite important, we tested the methods to predict data inventories, which is for the prospective assessment really relevant, I think. Biorefineries, so I think you have to analyze them case by case. We can't say the bio-based economy is good. We can just say these products from biomass are good and these are a bit worse. So I think we still have to stick to our old functional unit approach there. And we can see that often the environmental impact is better for the bio-based options because the climate change is an important factor in human health and natural environment, and of course fossil consumption for exhaustible resources. But there are exceptions, for example, the sugar cane which is burnt and results in particulate emissions, and eutrophication, for example, if you put the digestate on the field. And then the economic and social impact is less evident. It's not always it's not a clear system there. For example, the prosperity of domestic organic waste valorization is worse, and of agriculture is better. So it was a quite interesting exercise for us to do because we have these new insights and these new dimensions actually. So that was interesting to do for us as well.